Hello everyone, I'm Asif Shakar and I'm going to be presenting about hip exoskeleton modeling for the class Advanced Mechatronics. Let's look at the step-by-step mechanism for the hip exoskeleton modeling. On the left side you can see the electrical and mechanical part, in the middle with the transmission, and at the last the wearable structure. The equations that are formulated over here are converted into a transfer function which can be used to control the input and the output of the system. An actuator actually plays a very important role in the modeling of the exoskeleton. So let's look at what an actuator is. So an actuator is a device that produces a motion by converting energy and signals going into the system. The motion can be either linear or rotary. Those are the two types of actuator. And we can also see the three different paradigms of actuator in the bottom, and they're being compared. For this project, I'm going to be focusing on factors that affects the performance of the actuator, especially on the bandwidth and the backdriveability between the series electric actuator, or the SEA, and the quasi-direct drive actuator, or the QDD. So let's look at what is a bandwidth and the backdriveability. The definition on the screen are from the textbook, and in simple terms, backdriveability means the easiness of use from the humans or the end users, and a bandwidth means how fast a system responds when there's a change. So I use Simulink to get an analysis for the difference of these two in QDD and SEA. This is the control diagram of Simulink for backdriveability. And over here, we can see the two different graphs. On the left side is showed with the chirp input with 0 frequency and 16 seconds target time, where we can see the bandwidth, where we can see the backdriveability of SEA and QDD by looking at the amplitude of the resistive torque. So the lower the torque, the lower the friction, and the higher the backdriveability. So we can clearly see over here that QDD has a much more higher backdriveability than SEA. This goes same for on the right side too, where there's an input of initial frequency of 1 hertz and target time is lowered to 5 seconds, but still we can see that QDD has a much more lower resistive torque than the SEA, meaning QDD has a higher backdriveability than SEA. Next, I went on for the analysis of bandwidth. Here you can see the control diagram of Simulink for bandwidth. And over here, we can see the Bode plots from where we can find the magnitude at -3 decibels is where we can find this bandwidth for the system. Over on the left side, we can see the bandwidth of QDD on a chirp input of 300 hertz of initial frequency and a 30-second target time. We can see it's 154 at -3 decibels. And on the right side, we can see the the SEA bandwidth analysis for a chirp input of 300 hertz initial frequency and the same target time as the QDD, but it has a much more lower bandwidth than the QDD. This simply means that the QDD will respond faster to any kind of change in the system input. So from this project, I learned a lot about actuators and their importance in robotics generally, especially in exoskeleton modeling. And I also learned about the different actuator paradigms and how different factors such as bandwidth and backdriveability affects their performance. And also I learned how to use Simulink to do the analysis and get plots like Bode plots. But most importantly, I think from this class and from this project, especially, I learned that how theoretical control system, what we learned before, is used in real life application and the effects of it. So I want to thank you, especially Professor Hao Su, Shuang Yu, Selena, Hang, and Huang for helping us out, the whole class, and me out throughout the project and the class. Thank you.